Okay, welcome everyone. Thanks for coming, especially this is a late afternoon talk. We are here to talk about OpenCensus and our plans for Kubernetes. So first of all, let me introduce myself. I'm Jaana. I've been in this industry for a long time, and I'm pretty much of a really frustrated engineer. I've been working for 15 years almost, pretty much working on networking systems. And I went from company to company pretty much to do the same thing, like reinventing the wheel to scale how we develop and how we scale our production. My job just didn't really involve building systems, also making them more reliable and more debuggable. So we are all here at this conference for Kubernetes, and maybe it's ecosystem tools, right? But why are we actually here? Why did we all get interested in Kubernetes to begin with? Not for the sake of learning another tool. We are all here because these tools are making our lives better. An engineer's dream is to get things done and then go back home and sleep tight and maybe not interrupted because of an on-call. And if there's an on-call interruption, you want to be able to debug things and go back to sleep again, right? And this should be at the core motivation of everything we build, just making people more productive. But this is not really as easy as it sounds. And the main reason is our systems are getting more complicated. Most systems start really small and add up more complexity over time. Even if you have a really small size project, a really nicely scoped project, you end up actually growing in terms of complexity because you're dependent on all these new other things around. You're dependent on layers of infrastructure, software and hardware, which adds up to complexity. This is what it looks like nowadays. You have all these different layers. I call all these your code, frameworks, libraries, the user space, and everything underneath is the infrastructure. And cloud stack is becoming more complicated in the recent years. There was no Kubernetes a couple of years ago. Nobody really knows about the bare metal, to be honest. Few people in the world understands the kernel, and network stack is already too complicated. And now we have this cloud stack, and who really understands all this stuff? This is all of a black box for us, but we all need to rely on to get things done, right? Unfortunately, we are in a world where complexity is inevitable because of the growing dependencies. And even if it's not our system, it's just the things that we rely on is complex. Things fail in unexpected ways and in isolation. But in the end of the day, we're still in the charge of fixing them, understanding them when things go wrong. And if we can't do anything to reduce the complexity because it's out of our control, maybe we need better concepts and tools to understand what is going wrong when things are going wrong. So you may think that life is amazing and everything is well contained when you have a single pod, a single container. At this level, the problems are well contained, right? The boundaries are well set. This is a really nice abstraction, and it's a good isolation level. It looks really elegant, pretty, and simple. Several tools already exist to actually understand a singleton. You can depend easily on the Linux perf and diagnostic tools. Some of these tools probably. How many of you have heard about these tools or using them, like TCP dump, netset? Yeah, lots of you. The DNS diagnostic tools, typical perf, Linux perf tools. But then what happens? It's never as simple as having one single container, right? You have two of them. And when you have two of them, things are getting a little bit more complicated because you have some sort of networking in between. You need to talk. I simplify the situation here by just having two containers side by side, but imagine a long chain of different containers depending on each other. And the communication among them is not just networking. You may have different higher level components, such as message queues, maybe. You have all this different variety of different ways to trigger work. And then the storage comes into play. And everybody knows that storage is the most nastiest thing. Storage is the main root cause of all the problems, latency-wise, or hard failure cases. And occasionally, network is getting more complicated than you think because you are going out of your local network and coming back in. Sometimes you're going out of your physical location and coming back in. And you have a load balancer in between even internally in your network. And load balancers are pretty much getting more complicated if you're going to the external network. And load balancers do a lot of magic. The first magic they do is the load balancing decisions, and I'm not an engineer smart enough to understand them. The second one is like, the typical things that like retries and like rejecting requests and all sort of stuff. And when I put all these containers in naked forms, they looked really simple, but they are actually living on actual host machines. So these are like, it could be VMs running on VMs, and there's all this like different, networking, bridging, and so on. Like network stack is really complicated. There are endless failure modes when it comes to, talking about deploying containerized systems around. I just want to give you a few of them so you can understand the level of complexity. And all this stuff, in the end of the day, is this, orchestrated hot mess. Who understands Kubernetes end to end? I sometimes work with people working on Kubernetes, and they sometimes are surprised to see why things end up being in a state. It's unexpected. Things have failed in isolation. Even people you might expect to have understanding this, the entire stack end to end, doesn't truly understand what is going on. Are these problems unique to Kubernetes? Well, of course not. Like, these issues have been around for a long time, but I can say that they are really amplified. The first issue is the locality is now an issue because our workloads are distributed on a fleet of machines. We can't always really tell like where the actual issue is rooted at, right? Like which specific machine or VM. Networking, as I explained, is a huge, it's made of many components, and the network stack itself is already too complicated. Scheduling decisions are really complicated, and things always fail in isolation, and not a single person really understands. And service dependencies are not a new concern, but now we break down our monoliths much easier, and it really amplifies the problems of having more services as well as having more failure in terms of service dependencies. So I gave you a variety of these failure modes because in reality, you can't really assume that your pod is an isolated artifact. It really depends on all these layers and all these relationships, and all of them really matter. Let's take a look at these layers again. It's just too much to learn, many layers all scattered around, and nobody is a true expert on the entire stack. So pinging a server is the hello world of all networking problems. And as simple as it looks, I'm really surprised sometimes, like all the issues I'm going through when I'm pinging a server. And here, I actually have a ping client that is going to ping the Pong server. Pong server has been contributed by one of my coworkers already. So my job is to just really write a ping client and see what is going on. I will switch to my demo if I can. And so I already did some homework, and this is the simple main function I have. What it does is really it takes a instrumented HTTP client and makes an HTTP post to an endpoint. What it does is really simple. It just logs ping, makes a request, and prints the response. So the basics of the hello world networking example. And I use an instrumented HTTP client. As you see, it's that simple that I imported this package, and I'm using the instrumented transport instead of the Go standard library transport. So I already have a pod YAML, ping YAML for this, and it just basically just grabs this ping client and runs it. What I'm going to do is going to deploy this ping. And I actually have a deployment now. If I take a look at my pods, I can see ping is running. It's awesome. I already, as I explained, there was Pong. So Pong is already running in this cluster. And now I can take a look at my logs to see if things are working correctly. Let me actually follow this because, As you can see, that it actually started to work, and as I was expecting, it's actually doing some sort of like what I was expecting, like printing a ping, and then like I'm getting a pong as a response. If you take a look at our pong server, it just really responds with pong, so it's working as expected. But there's actually one thing that I haven't expected, which is like once a while, it just prints out this like empty string, which is not what I was expecting. And it's kind of funny because the handler really hard code to respond, so there's no reason that like it's actually like responding with an empty string. So since I can't really truly understand what is going on from my logs, what I will do is to switch to some other diagnostic tools. In this case, as I was telling you, I instrumented already with a client that can give me some distributed traces. And here, what I can do is to understand what actually happens in the lifetime of that request, in that ping request. What I will do is to click one of these, and as you see, this is a distributed trace, and it explains what happened in the lifetime of that request. And it's funny because I was expecting that, like, hey, this is a really simple case. I'm just sending an outgoing request, and like it's going to be handled by the Pong server. But you can see that there's actually a lot more going on. And none of this actually, what is going on here, was visible to me without distributed traces. So I can see that, like, I'm sending a request, and it's actually hitting a load balancer rather than directly going to the server itself. And then there's a decision made here, and you can see that there's actually a new target, and then the load balancer is proxying the incoming server request to the actual target and making the request. And at some point, it's actually going to the Pong server, and Pong server in this case is responding in like 32 nanoseconds, and everything is just being proxied back to my ping client, and at some point, I actually print the response. So all this stuff was really new to me. And if you actually take a look at all these like events, there's more going on in terms of network, and I'm doing all this like crazy like connection pooling and like resolving the DNS, which I couldn't see here, but I can see this level of detail by looking at my distributed traces. One thing I haven't seen here is like this is not a failed case. So maybe let me filter by HTTP status 500 to see if I can figure out an error case. If I click on this, maybe hide the events. So this actually looks a little bit different. As you remember from the first trace, I was sending one thing, and then the load balancer was responding, and it was being received. In this case, there's, again, this load balancer. But as you can see that there's other things going on. This proxying thing has failed, which was not visible to me from the logs because logs didn't capture that level of detail. But it says that like it couldn't dial this particular target because there's no such target around. And it tried 3 times to send a request, proxy the request, but it couldn't. And then I ended up failing, and it responded me back with 500. But the funny thing is, like, in my logs, I was not able to see it because I am a terrible programmer myself. Now I realize that going back to my client, I didn't really handle the error here. So the client post is actually not returning me an error, but the response is a 500 response. So I should have like put here something like, hey, if response status code is different from 200, just log some error. But I failed because I was not really paying attention, and my code reviewer was probably not doing a good job. So what happened is I was able to, I realized something that I couldn't gather from logs or anything. Our team rolled out a custom load balancer. It was in our stack. I didn't know about it. I learned it because we had distributed traces. I had this like miss and error handling case, and I was not logging a message about that case at all. And I was able to see it, and now I can actually fix my code. And our load balancers, in the end of the day, was doing a poor job. It was trying to go to a target that didn't exist. So it's funny. I can't do anything about this because I'm not the maintainer of the load balancer, but what I can do is to quickly escalate it to the team working on the load balancer. So 3 things solved by just having this type of visibility. A while ago, we open sourced a set of instrumentation libraries that is used to instrument the traces that you have just seen. And this is now a project contributed by a variety of cloud providers and APM companies. We have these first-class goals of providing correlation between different signals. Distributed tracing is just one of them. And I want to leave the mic to my coworker Morgan now, so he can explain more details about what we are doing in that space.
Thanks, Jaana. So in Jaana's demo, you saw how she was able to instrument and get traces out of her application with just a few lines of code, right? And so what was happening there is OpenCensus automatically has an HTTP handler in Go, and with that, it handles context propagation and also captures traces and spans. So it's a really easy way to instrument your application. As Jaana mentioned, my name is Morgan McLean. I'm a product manager at Google. I've been on the OpenCensus project since the very beginning. About 1 year ago in KubeCon Austin, we sort of announced OpenCensus to admittedly a much smaller room than this, so I'm glad the community has grown quite a bit. Since then, we've had a number of other companies, a number of other organizations join the project. We have a lot of contributions, and it's really, really grown and gained a lot of momentum. Some more background, OpenCensus is a set of instrumentation libraries that allow you to capture traces, so distributed traces, propagate context, and capture application metrics. That includes typically automatic HTTP or other RPC metrics, as well as custom metrics that you can define. So let's extend Jaana's example to a more typical e-commerce application. So here we're looking at about 4 services. Typically an e-commerce app would have more than 4 services, but that's what we're going to look at today. And we've drawn up some of the interactions between them. Just like in our demo, one of the challenges is getting information and getting telemetry out of these services. And as Jaana demonstrated, we can use the OpenCensus libraries to do this. We have libraries across 7 languages. You link them to your application, rebuild, redeploy your app, and they'll try and capture as much telemetry as possible. If we can't capture it automatically, you can either add instrumentation to the OpenCensus libraries, and please put in a pull request to GitHub so everyone else can take advantage of it, or you can just instrument your own application, have it use the OpenCensus APIs to send data there. Not super fancy, probably not a sort of a wild concept to anyone here. There are some limitations here, though. Primarily, OpenCensus, because it's running in process as a library, can't capture system metrics. So you can't capture like system CPU consumption or anything about the host that you're on. Secondly, if you want to switch exporters, so OpenCensus can send metrics and telemetry to various different backends. If you want to change which backend you're using, you'll have to recompile and redeploy your app, which is really, really annoying. It's especially annoying if you are providing a platform like Kubernetes itself, right? Like if you're a cloud provider or even a company that uses Kubernetes, if you're switching export targets, you probably don't want to have to like rebuild all of Kubernetes. That's sort of not desirable. And to that end, we've created the OpenCensus agent. So this is an optional component. You can still export things directly from the OpenCensus libraries. But what it does is it runs on every VM or every Kubernetes pod or really every host that you have. And you can have the OpenCensus libraries send telemetry to the OpenCensus agent, which can then send them to your metrics or tracing backends. The advantage of this is that you can change exporters on the fly without rebuilding or redeploying your app. It also means that it can collect system telemetry, particularly system metrics, and send those to that same backend. So it's a huge extension of the existing OpenCensus ecosystem. And as I mentioned, this is completely optional. This is in beta. I think we have a few customers using it. It's on GitHub. It's definitely usable, but there's more work coming. The system metrics part isn't there quite yet. And finally, we have the OpenCensus service, and we're about to do a demonstration of this on stage. The OpenCensus service is another optional component. You can run it as a service inside of a Kubernetes, or really anywhere else you deploy a container. It runs as a network service, and you can send your traces and metrics and other telemetry to the service, which will then send them back to your backend of choice. So it's just another layer of aggregation. But it also brings in some of its own really powerful features. The first is tail-based trace sampling. So typically when you sample traces in an application, you need to sample them, make your sampling decision at the beginning. This allows you to make the sampling decision after the traces are captured. So you can get much more interesting traces sent to your backend. So this is like incredibly, incredibly powerful. Next, you can change your exporters more easily. You can do it fleet-wide. And finally, OpenCensus includes a feature called Z-Pages, where you can sort of get this fire hose view of everything that's happening right now. This lets you do it across your entire cluster, which frankly makes them actually really useful. This service is in alpha, so it's also on GitHub, but it's probably not ready for prime time quite yet. But we're going to do demo it anyway, and we think it'll be production ready pretty soon. So I'd like to introduce Steve from Omnition to do the demo.
Thanks, Morgan. So for those of you that don't know me, my name is Steve Flanders. I am head of product and experience at a stealth startup that you probably haven't heard of called Omnition. And while I'm not going to talk too much about what we're doing today, what I can say is that we are contributors and maintainers of the OpenCensus repository with Google and others. So just to summarize really quickly what Morgan was talking about with the OpenCensus service, it's made up of two different components, the agent and the collector. And there's a variety of different use cases for why this service exists. Now, these two components live with your application, and you can send to a variety of different backends. There's a variety of different reasons why you want to do this. The biggest is when you're adding instrumentation to your application, you want to do it once. You want to kind of set it and forget it. And so you can do that with the OpenCensus service because you can lazily configure anything that you want in terms of exporters, sampling policies, and more. And that's what the OpenCensus service is trying to solve here. It does so by having two primary components, receivers and exporters. As the names imply, receivers allow you to get data into the system. Exporters are a way of getting data out of the system. All right, so there's a healthy ecosystem of options here for receivers and exporters, for both traces and metrics. Here are just some of the ones that are available today in the OpenCensus repo, and of course, you can contribute your own as well. The goal is to provide flexibility. With a standard in place, all you have to do is write a single exporter, and you can then leverage the power of OpenCensus. Now, what I want to talk to you about is something in the OpenCensus collector specifically. It's the problem of traces, which is they are extremely verbose. There are a lot of them. They're extremely valuable, but there's a lot of duplication. For example, you probably want to see some of the HTTP status 200 messages that are coming into your system that are being traced, but do you need to see all of them? Well, I mean, if you can compute things like latency and you can only get traces like errors that you care about, you don't need to get every single event. That's where sampling comes into place. The primary way of handling sampling today is something known as head-based sampling. This happens either at the client or at the agent level. It's a sampling decision that when the trace is being instantiated, when the first span is being created, a decision is made on whether or not we're going to actually sample that event and send it to our backend of choice. This is great. It's extremely powerful. It allows us to limit the data that's coming into the system, but it has some limitations. Because we're making that sampling decision when the trace is being instantiated, we don't know what actually happens downstream in that call. For example, if the next span, the next service that I call has an error, I may not receive that error because I made a sampling decision that said drop that event. So to solve this problem, there's something known as tail-based sampling. The idea here is I actually collect the entire trace and all the spans in it, and then I make a sampling decision. This is powerful because I can have a variety of different policies that dictate whether or not I want to sample this event. A very classic example is the error-based. So if a trace has an error, maybe I want to sample 100% of those, whereas if it's not an error, I can use a different head-based sampling policy. But that's really just the tip of the iceberg. You can actually do some much more interesting things as well. For example, these retrieval-based sampling policy. The idea here is maybe I decided not to sample this. I can still keep that trace in the collector, and I can ask for it later, maybe a minute later, 10 minutes later, an hour later. So the trace isn't actually gone. I chose not to sample it, but if I then realize I need it, I can still get it back out of the system. OK, so I'm actually going to demo this. This is a feature that's going to be upstreamed to the OpenCensus service repo here in the coming weeks. What we have right now is a prototype that I can show you live. So in the OpenCensus service, we use something called the hipster shop. It's a demo application, and it has a topology. That topology could then be replicated in some sort of load generation tool. So we've written a load generation tool. It's JSON configuration based, and right now it mirrors the hipster shop, but you can actually write your own configuration, your own topology for your environment as well. Then what we've done is we've pointed this log generation tool at the OpenCensus collector. The OpenCensus collector receives it, and it's been configured to send to two different destinations. Since I'm going to be running this locally, I'm sending to two separate Jaeger instances. And you can, of course, try this out, too. Everything I'm about to show you is publicly available right now. It will be upstreamed in OpenCensus repo in the coming weeks. So if you haven't seen the hipster demo app, it's basically a web application. It allows you to, it's basically a marketplace where you can order some cool hipster items. It's actually a polyglot, microservices-based distributed architecture. It's written in a variety of different languages. This is also available on GitHub. You can play with it. It's a way of actually sampling all of OpenCensus capabilities. So what we've done is we've taken that topology on the right-hand side there, and we've created a configuration for it. And so what I'd like to do is go ahead and demo that for you. Okay, so that topology that you saw on the right-hand side, here's a more live representation of it. So you can still see all the services. The errors here indicate the amount of traffic, the amount of requests per second that are being sent, and anything with red indicates errors in the system. So this is synthetic data that the load generator is sending to the OpenCensus collector. And what I want to do is make a sampling decision based on the types of traces that I'm receiving. So let's go ahead and do that. In the demo application, it's a little bit small. Let's try to make it a little bit bigger for you. We have a Docker Compose file, and this will actually spin up a Cassandra instance with 2 different key spaces, because we've deployed 2 different Jaeger instances. And so what we've done is we've configured the load generator to send to the OpenCensus service. The OpenCensus service has 2 rules. One to send all events to a single Jaeger instance, and one to only send error traces to the second one. Let's go ahead and take a look at what that looks like here as this system comes up. So it takes about 10 seconds or so, and then you can see right now it's emitting trace IDs. This is going to actually represent that visualization that I just showed you. Let's pull it up. So it actually exposes 2 ports. It exposes 17,000, which is a Jaeger instance that's receiving all of them. So for example, I'm looking at the checkout service here, which is one of the hipster store applications. You can see here that I have some traces that have no errors in them, and I have some traces that do have errors in them. So this is the Jaeger instance that the OpenCensus collector is sending 100% of the traces to today. Basically no sampling policy in place. Great. There's also a second one running on port 18,000. This one also has the checkout service, but notice that there are no success events. There are only errors. That's because there's a tail-based sampling policy in place that says only sample the error events and drop everything else. This is the power of tail-based sampling in just a single example. There are several other policies that can be written here. So just at a high level to kind of show how this works, the actual topology generation is JSON configuration base. You can see an example of it here. You can write your own. And then on the flip side of that, there is YAML-based configuration for the OpenCensus service. So here you can see that there are 2 policy rules. There's one where we're actually doing it based on tags, another one where we're doing it on HTTP status codes, errors, for example. And this can be extended to a variety of other use cases that I was highlighting before. So with that, I'll turn back. And everything that was just demoed will be up on the OpenCensus repo here in the coming weeks. And with that, I'll turn it back over to Morgan to wrap it up.
Thanks, Steve. Thanks, Steve. That was fantastic. So I want to wrap up today by talking about 3 other important tasks that we're working on. So in addition to everything that we've shown you, this is only a 35-minute presentation. There's some other items that we want to talk about. The first is there's a lot of questions that we've received throughout the life of this project about what's the difference between OpenCensus's tracing API and OpenTracing. We've been meeting pretty regularly with the OpenTracing group to try and come up with a common API. We actually had a meeting, I think, 2 days ago, early in the morning, and we're on a pretty good track. We're really excited about the progress we've made, and hopefully we'll have more to share pretty soon in the new year. Next, in 2019, we're also adding client-side instrumentation to OpenCensus. So today, OpenCensus, like many other tracers, focuses on tracing your backend systems, things running inside of a cloud provider, things running inside of your data center. What we're adding, and there's already a prototype out today, is instrumentation for front-end web applications. So you can get spans in your traces that are emanated from client apps, and so you can see like client latency and the amount of time it takes for a lot of UI events in your clients. Later in 2019, probably late 2019, we'll be adding support for Android and iOS as well. Finally, we're in the middle of a design process for OpenCensus logging. I don't have a lot of time to talk about this today. We've already met with a lot of larger OpenCensus users and vendors, but if logging and sort of new logging APIs and new logging technologies are something you're interested in, please stay behind and chat with us. And with that, we're done. So thank you very much for attending today. We really appreciate it. Our goal has always been to make this project as open as possible, and we have a really big and growing community. There's a number of us here from Google, Microsoft is one of our biggest partners, Sergey's here from Microsoft, Omnition, and other partners to stay here and chat, answer questions, and just hang out. So with that, thank you very much.